Hello, hello. Testing. Okay, sorry, my mic wasn't plugged in. Hope you all are well. So let me know if you can hear me. Today I wanted to do a couple of problems, all involving, well, maybe like 4 or 5 problems, all involving generating functions, essentially. So generating functions, the idea is very simple. You have some sequence that you're interested in. Usually it's some kind of combinatorial sequence, some sequence arising from combinatorics. So you'll have like some sequence A0, A1, A2, and so on. And what you do is you essentially store this sequence in a function. So you just write A0 plus A1x plus A2x squared plus A3x cubed, and so on. So the thumbnail suggests you're only wanting Americans to watch, so I won't bother. That's very funny. So you should be able to make change for any amount in any amount coins. I just threw the thumbnail together quickly. So I hope you stick around. In any case, if there's a sequence that you're interested in, you store it essentially in a function like this. So, A0 plus A1x plus A2x squared plus A3x cubed, and so on and so forth. And then sometimes, if you're lucky, this expansion has a compact form. Like maybe it happens to be the Taylor expansion of some function, or maybe it happens to be something you can see rather quickly. And so you can sometimes write this as some compact function f of x. Now the whole idea is that you essentially play one way of writing things against the other way of writing things. So there are things that you can do on the left and right hand side easily. I mean, sometimes you can differentiate this function. Sometimes you can integrate this function. You can multiply two of these together and something very interesting happens. And so there's all sorts of things that you can do in either case. And so that's the whole idea of generating functions. So a classic example that I could give you, well, actually, let me first state the problems that I'm going to solve with generating functions. So number one, I would like to explain how you would use generating functions to calculate your mortgage payment, which is kind of interesting that you can do this. Actually, the method I'll use to calculate what your mortgage payment ought to be is going to be the same method that one might use to basically give the compact form for all sorts of recurrences. Okay, so there's that. So the method that I use to show you how to calculate your mortgage payment is going to be the same method that you can use to essentially solve recurrences in general. Not every recurrence in the universe, but a lot of recurrences. Okay. The second problem that I'm going to solve is there's this dice problem called the Citterman's dice question. And the question is, can you construct 2 die, both of which have 6 sides? You have to write positive numbers on all of the sides. And the idea is when you roll them, the number of ways to get each sum has to be the same as it is on standard die. So for example, if you take 2 standard die, you'll see that the numbers on them are, 1, 2, 3, 4, 5, 6, right? And so you have 2 die, so the second one is also 1, 2, 3, 4, 5, 6. And so the number of ways to, for instance, roll a 2 if you roll 2 standard die is 1. There's only one way to roll a 2. The number of ways to roll a 3 on by rolling 2 standard die is 2, because you can do a 1 and a 2 and a 2 and a 1. The number of ways to roll a 4 on 2 standard die is going to be 3, because you can roll a 1 and a 3, a 2 and a 2, and a 3 and a 1, and so on and so forth. And so the question is, can you construct a different pair of die, again, 6 sides each, and you need to fill out these numbers, and they need to be positive whole numbers. And the question is, can you fill out these positive whole numbers in a way? Hello, Mohammed. How are you? So I'm not sure if you heard this question. So you have two. The question is, if you take two standard die, right, there's a certain number of ways that you can roll any given number. So for example, if you roll two standard die, there's only one way to roll a 2. There's 2 ways to roll a 3 because you can have a 1 and a 2 and a 2 and a 1. And then there are 3 ways that you can roll a 4 because you can do a 1 and a 3, a 2 and a 2, and a 3 and a 1, right? So the question is there another way to construct 2 6-sided die so that these totals are the same? So you still want there to be 1 way to roll a 2, 2 ways to roll a 3, 3 ways to roll a 4, 4 ways to roll a 5, 5 ways to roll a 6, 6 ways to roll a 7, then 5 ways to roll an 8, and so on. So can you fill in 2 6-sided die with positive whole numbers in a different way so that the number of ways to get the various sums is the same as it is with 2 standard die? Okay. The third problem we're going to do is we're going to talk about the number of ways to make change for a dollar. And so the interesting thing is we're going to actually do this in 2 different ways. So the change for a dollar problem. So we're going to do this first in the situation where order matters. So for example, you can imagine you're making change for a dollar. And so let's say you're making change for 3 cents. Or, well, no, not 3 cents. Let's say you're making change for 6 cents. And if you're making change for 6 cents, you might want to count it differently if you use like a 5-cent coin and a 1-cent coin versus a 1-cent coin first and a 5-cent coin second. Okay, so there's 2 separate problems here. There's a change for a dollar problem in 2 separate cases. One is the case where order matters, right? And the second is the case where order does not matter, okay? Okay, so you have a situation where order matters. Yes. We're going to do something. Well, we're probably not going to go. I've seen that video. It's a lovely video. And so he essentially figures out what happens. So you can use generating functions to get a general formula for the number of ways to make change for a whole dollar amount if you have more than, I think, $4, you can come up with a general formula. And I believe he derives that formula in his video. His video had a slightly different purpose. I'm basically trying to sell you all on generating functions because you can, so he mentions generating functions at the very end of his video. But my purpose in this video is to just sell you on the idea that generating functions are amazing. They're extremely powerful. You can use them to solve like a very wide array of problems. So you have the mortgage payment problem, you have the pairs of die problem, and you have change for a dollar where order matters and order does not matter. These are 2 separate problems. I believe Mythologer did the one where order does not matter, which does happen to be the more interesting problem. So if there are no questions about this, we can dive into the first question. So first of all, I hope you all find it interesting that it is possible to use essentially a similar method to solve all 3 of these problems. It's kind of surprising. It's kind of interesting. So first of all, let's solve the mortgage payment problem, okay, using generating functions. How might we use generating functions to solve the mortgage problem? What is the mortgage payment problem? I mean, how do mortgage payments work? And why is it a little bit tricky to calculate what your mortgage payment ought to be? Well, the reason it's tricky is because as you're paying down your mortgage, the bank is still applying interest to the amount that you owe. Okay, that's what makes it tricky. So you can imagine, let's say you owe $100,000 to the bank. Okay, and let's say you're paying off $1,000 every month. Let's say, if the bank is charging you, let's say 2% interest per month. Okay. What's going to happen is, from this $100,000, you take off $1,000, and so now you owe the bank $99,000. but then the bank will apply the 2% interest to the $99,000. Okay, and so this will keep happening every month, which is what makes it a little bit tricky. Okay, so let's come up with a problem with like relatively realistic numbers. By the way, there are different ways to solve this problem. Some of them involve formulas that are a bit more intuitive from an economic sense. But I'm just going to throw in numbers and just see what happens. So let's say you're a rich person. You're buying $1 million house. So I'm just trying to use easy-ish numbers. So the cost of the house is $1 million. So 1,000,000. Okay. This is the price of the house that you are interested in. Okay. Let's say the bank charges 12% per year, and I'm going to simplify that to 1% per month. Though be warned, there are different ways banks do that simplification. Okay, so let's say you're charged 1% interest per month. So the question is, how do you figure out how much you need to pay every month if you want to pay this amount down in, let's say, 30 years? A reasonable term for a mortgage. Okay, so once again, let's be very clear about this. So the amount that you owe at the start. So I'm going to just define a recursively occurring sequence. So A0 at the very start is going to be 10 to the 6, right? $1 million. And now what happens in the first month? Well, in the first month, you do 10 to the 6 minus M. Okay, so you get rid of, so let's say M is your monthly payment. Okay. Okay, so you get rid of M off of 10 to the 6 every month, but of course, the bank will also apply interest after you're done making the payment. By the way, you can set this up so that the interest is applied before or after you make your payment. It doesn't really matter. This is a universally applicable method that you can use to solve all sorts of recurrences. So you can set this up however you like. I'm going to set it up so that you do your monthly payment first, and then at the end of the month, interest is applied to it. Okay, so then you would multiply this by 1.01, because if the bank is charging you 1% per month, then the amount will go up by, you need to multiply by 1.01. It's a 1% interest plus whatever the original amount was. That's why you're multiplying by 1.01. Okay. In the next month, what's going to happen? Well, this is now what you owe. Agreed? This is what you owe. And so, again, you'll have 10 to the 6 minus M times 1.01, and then you subtract off another monthly payment, but of course the bank charges an additional 1.01 in interest. Okay? So if I were to summarize this pattern in a simple formula, I would just write that, the amount left in the mortgage, month n plus 1, is just going to be, I would say 1.01 times whatever was left on the mortgage in the previous month, minus whatever your monthly payment is. That's it. That's the recurrence. Okay. So whatever's going on in the next month is you take the previous month, you subtract M, and then you apply the interest. Let me know if there are any questions about that. So this is the recurrence. Okay. Now, the question is, of course, how do you solve recurrences, right? And so my claim to you guys was recurrences are relatively, all sorts of recurrences are easier to solve. I'm to be honest, there are easier ways to solve this particular recurrence than the way that I'm going to do. But the nice thing about the method that I'm going to use is you can use it to solve a very wide, like a wide array of recurrences. Okay, so you have this recurrence. Okay. And once again, the idea of a generating function is if you have a sequence that you're interested in, like A0, A1, A2, A3, and so on, you store this sequence as a power series, essentially, okay? You store this sequence as a power series. So you turn it into A0 plus A1x plus A2 x squared plus a3 x cubed, and so on. Okay. We're trying to find m so that a30 is 0. That's absolutely true, Mohammed. But also what we are doing, when we're done, we should have a direct formula that should tell us how much we have left in the mortgage every month. Okay? So basically we have this recurrence, right? And what we're after at the end of the day is an explicit formula. So a formula that will, if I give you the month, will just tell me, right, what it is. Also, one minor correction. It wouldn't be A30 equals 0. It would be like A360 equals 0. Okay? Because you would want, it's because 30 years. Wait, how many months are in 30 years? Yeah, it's 360 months in 30 years. Okay. So this is the idea. You know, you have this, right? Okay. And the idea is sometimes, you know, you just write this as a function, capital F of x, and you play off the concise formulation on the left with the expanded formulation on the right. And, you know, hopefully interesting things happen. So I'm going to use the summation notation here. Hopefully it doesn't scare anyone off, but you can write this as the sum, right? N greater than or equal to 0, a n x to the n. Hopefully that makes perfectly reasonable sense, okay? So there's two ways to write this concisely. I can write this whole thing as capital F of x as a single function. I can also use a summation notation, which is the sum n greater than or equal to 0, a n x to the n. And please let me know if there are any questions. Okay. So here's what I'm going to do. So I basically want to use this recurrence, right? And I'm going to show you a general method. So basically what you can do is you can say, if I start adding n greater than or equal to 0, let's do a n plus 1 x to the n plus 1. This is almost f of x, but you'll notice it's missing the first term. So if you were to expand this out, for example, this would start at 1. This would be a1x plus a2 x squared plus a3 x cubed, and so on. Now the reason for this is because we're starting our index at n greater than or equal to 0, but when you plug in a 0 into the sum, it starts at 1. So hopefully that makes sense. Now I can use my recursive formula, right? And so this is, you know, just the sum of n greater than or equal to 0 of, you know, 1.01 an minus m x to the n plus 1. All right? Let me know if that makes reasonable sense. All I did was plug in an plus 1 equals 1.01 times an minus your monthly payment, which is m. Okay? Hopefully perfectly reasonable. All right. So now this is going to be, well, you can simplify this out a little bit further. So this is going to be, let's see, I'm just going to expand out the sum. This is n greater than or equal to 0, 1.01 an x to the n plus 1, okay, minus m. Is sum n greater than or equal to 0 the same as sum 0 to n, asks Ken. Not quite. N greater than or equal to 0, by this I mean 0 all the way to infinity. So for every single number that's greater than or equal to 0. So just do 0, 1, 2, 3, 4, 5, 6, 7, just keep going forever. It's an infinite power series, okay? Hopefully that makes sense. All right. So then this would be m times x to the n plus 1. This is also n greater than or equal to 0. Okay. Seems like a very fancy way of figuring out what your what your mortgage is, but I swear there's a payoff here. So move this up. Actually, I might make a little bit more room for myself. Hopefully you all remember what the situation is. It's $1 million house. They're charging 1% per month. And so this will be the recursive formula that tells you what you owe at the end of every month. Okay. And I forgot the 1.01. That is absolutely correct. Thank you, Matthias. I hope I'm saying your name correctly. I appreciate that. So this should be deselect 1.01. All right. I'm just going to tidy up the board a little bit just because I'm running out of room. Okay. Just going to take this and put it up. Well, I'm going to put it up here. I'm only slightly covering it. Okay, just minus 1.01 m, the sum x to the n plus 1, n greater than or equal to 0. Okay, now we're doing well. Okay, notice the sum on the. Hey Brian, hope you're well. So we're figuring out mortgage payments right now. So the sum on the left-hand side is the same as just f of x, but it's just missing the first term. So I'm just going to write f of x minus a0. A0 in this case is $1 million because it was $1 million house. Okay. And now this thing is going to be, I can take a 1.01x out, 1.01x, and this is just going to be the sum n greater than or equal to 0, an x to the n. Okay? So, by the way, the sum n greater than or equal to 0, an x to the n is just f of x, right? But that seems reasonable. And then I can also take an x out of this one. I get negative 1.01 mx, and the sum x to the n as n is greater than or equal to 0. Let me know if there are any questions about what I've done so far. Okay. By the way, this has a closed form. Let me expand this out. So this is just, n greater than or equal to 0. You're summing x to the n. So this would be like 1 plus x squared plus x cubed and so on. Okay. And you might remember, this is just the Taylor expansion of 1 over 1 minus x. Okay? So I can just replace this with 1 over 1 minus x. So you're already seeing the interplay between writing things in their kind of compact form versus the infinite series form. So I'm actually just going to replace this with over 1 minus x. Okay? Hopefully it seems quite reasonable. So now I'm going to solve for f of x. Okay, so I'm just going to take all my f of x terms on one side, and all my non-f of x terms are going to be put on the other side. So it's going to be 1.01 mx. Okay, over 1 minus x minus a naught equals. So the f of x is going to be times 1.01x minus 1. Also, please check everything I'm doing. I'm notoriously prone to arithmetic errors. I'm just warning you all right now. But the method should all make sense. Okay, so you have the situation. So now if you just divide both sides by 1.01x minus 1, this should give you what f of x is. Okay, so but before I do that, I'm just going to take the common denominator on the left. So I have 1.01 mx minus a naught plus x, and then divided by 1 minus x, and then times 1.01 x minus 1 equals f of x. Okay, so it turns out if you just Taylor expand the left-hand side, or if you ask your computer to Taylor expand the left-hand side, the terms in your Taylor expansion will tell you at every month how much you have left to pay down on the house. which is kind of interesting, right? So yeah, if you just Taylor expand the left-hand side, then the coefficient of x to the n in that Taylor expansion will tell you how much you have remaining to pay so Weeksaw says, what is the plus x from on the left? I just took the common denominator between 1 minus x. So this 1 minus x, and it's like a naught over 1. So when you do that, it becomes minus a naught. Oh, thank you. You caught me. It should be plus a naught x. So thank you for that. Plus a naught x. So thank you for that catch. But let me know if this makes sense now. All I did was take the common denominator on the left-hand side, and I appreciate the catch. Okay. So interestingly enough, if I just Taylor expand the left-hand side here, it will tell me the coefficient of x to the n in this Taylor expansion is going to tell me precisely what I have left on the house. But there's another thing we can do here to make our life a little bit easier. I mean, if you're at the bank, you probably don't want to be computing the Taylor expansion of this function to figure out how much money you have left on the house. So let's keep playing around with this and see what we can get. If you remember in calculus, if you need to integrate or Taylor expand a complicated function like this, a good method to do it is using partial fractions. Okay? So partial fractions is when you have a product in the denominator. Okay? When you have a product in the denominator, what you do is you re-express it as a sum of, wait, no, never mind. You re-express it as a sum of two fractions, right? You re-express it so that one fraction has a denominator 1 minus x, and the other fraction has a denominator 1.01 x minus 1. And there'll be something in the numerator here and something in the numerator here. Yes, Taylor expansion around 0 will indeed give it to you. But let me finish this before you start Taylor expanding at the bank. Let me just finish this partial fraction business. Okay. So and in essence, we are after what A and B are. Now you've already seen the quality of my arithmetic. It's not fantastic, so I'm just going to use the computer to do. Yeah, I'm just going to use the computer to do partial fractions. So Mathematica has a nice partial fractions calculator, and that's what I'm going to do. So the Mathematica function, by the way, you can also type this into Wolfram Alpha, I believe. You just type apart, and then in the numerator, you do 1.01 mx minus a naught. A naught in our case was $1 million. A naught x, and then you divide by 1 minus x, 1.01 x minus 1. Okay, so do that. Okay, it has partialed. We have partial fractioned our expression. So let me just copy in what Mathematica said. This is what Mathematica does, and you know, it writes things in a form which is not 100% what we want, but it's still way easier than doing partial fractions ourselves. So what Mathematica said is that this will turn into, let's see, 101 times m over x minus 1. Oh, I'm sorry, times 1 minus x. Okay, and then it's a little weird. Hold up. So this is, so Mathematica is saying plus negative 1 over 1.01 divided by negative 1 over 1.01 plus x. And then in here goes a naught minus 101m. I have no idea why it chose to do the 1 over like this, but it's okay. If I take a negative 1 over 1.01 common in the denominator, this denominator will turn into negative 1 over 1.01 times 1 minus 1.01 x, which is very good, right? It's about what we wanted over here. So I'm just going to put that in the denominator instead. Over here. And I swear there's a mortgage payment coming very soon. Okay. Deselect. Okay. And now you can just, you can cancel these terms, right? So I'm just going to cancel these two. Okay. So everything I've done so far is just partial fractions. It's going to seem quite mysterious to you if you are like uncomfortable with, or maybe you've never done partial fractions before. But if you have, it'll seem quite reasonable. Okay, so now we're really cooking, because the thing at the top had a really kind of nasty Taylor expansion, but the thing at the bottom has like a really like almost a trivial Taylor expansion. We already know what the Taylor expansion of 1 over 1 minus x is, right? The Taylor expansion of 1 over 1 minus x is just 1 plus x squared plus x cubed, and so on, right? So this is 1 plus x squared plus x cubed. And of course, we're multiplying this whole thing by 101m. Okay? What's the Taylor expansion of the thing on the right? Well, the Taylor expansion of the thing on the right is just a naught minus 101m, right? Times, okay, what's the Taylor expansion of 1 over 1 minus ax? Does anyone remember? So the Taylor expansion of 1 over 1 minus ax is just like 1 plus ax plus a squared x plus a cubed x, and so on, right? So plugging that in here, I get that this expands to, of course, 1 plus 1.01 x plus 1.01 squared x, and so on. Now, while this might seem like a mess, here's the thing. If you look at the coefficient of x to the n in this sum, that'll give you an explicit formula for how much you owe. So what is the coefficient of x to the n here? I'm just going to erase some of the old work so you can see. What is the coefficient of x to the n here? The coefficient of x to the n here is 101m. Okay, from the top, that's the coefficient of x to the n. And at the bottom, the coefficient of x to the n is just 1.01 to the n times a naught minus 101m. How about that? What a lovely little formula that tells you how much you have left in your mortgage at the end of the month. And notice we did it all using generating function. So maybe do the generating function part at home and just take the formula to the bank if you're getting a mortgage. So let's see, first of all, let's see if all these shenanigans that we did actually work. Okay, let's see if they actually make sense. So I'm in Mathematica again. So let's first do it the recursive way. Let's say you're paying $1,000 a month. Okay, $1,000 a month. So I'm just gonna say, so if you're paying $1,000 a month, you start out owing. I'm just gonna write 10 to the 6. Okay. So this is how much you owe. A0. This at the start of your mortgage, you owe $1 million. A0. Okay, and then you pay $1,000. Right? But then the bank charges you that 1% monthly interest. Okay, so this would be your situation at the end of the first month. A month later, your situation would be subtract another 1,000 and multiply by another 1.01. Okay? A month after that, your situation would be you subtract another 1,000, okay, and then multiply by another 1.01. So this is what would happen if you were only paying $1,000 in a month. At the end of 3, so this is 0, 1, 2, 3. Yeah, this is what you would owe at the end of 3 months. So one thing you notice very quickly about this situation is $1,000 a month is not enough for this mortgage. If you're only paying $1,000 a month at 1%, the amount you owe actually goes up every month. Okay, but I want you to notice how ugly this computation is. And now let's try the formula. So the formula is just do 101 times 1,000, right, plus 1.01 to the third times a million, which is 10 to the sixth power, minus 101 times 1,000. Boom, the exact same number. So this really is an explicit formula that tells you how much you owe at the end of an n-month period. Okay, so to go back to my original question, which is how do you figure out your mortgage payment if you want to be done with your mortgage in 30 years? 30 years is, I believe, 360 months, right? So in order to solve for the mortgage payment that would allow you to be done in 360 months, you would just need to solve this equation, right? You would need to do 101m plus 1.01 to the 360 times 10 to the 6, because that's what you start, minus 101m equals 0. And this is just a linear equation, right? There's no... there's nothing, this is just a linear equation. I mean, I'll solve it for you right now. So you just do, I'll just ask the computer to solve it. But so solve, well, I'll do n solve. So you can just do 101m plus 1.01 to the 360 times 10 to the 6 minus 101m equals 0. Please solve for m, and m is 10,184. So if the bank is charging you 1% every month at the end of the month, and you pay at the beginning of the month, then you would have to pay $10,184 per month to be done in exactly 30 years, assuming this setup. But of course, you see, like, there's no you could plug whatever numbers you wanted. In fact, I kind of regret using only 1% here. You can adjust this formula for, I mean, you would have to redo the generating function computation to make sure nothing goes wrong, but you can adjust this formula however you like. Okay, so all right, see you in a bit, Brian. So hopefully that makes sense. So so I was trying to convey to you the power of storing the sequence that you are interested in a series, and I hope that I have convinced you. You can use this to solve all sorts of recurrences. So for example, we did this a little bit with the Fibonacci relation the other day. So for example, if you have a, well, maybe I won't get into it, but the Fibonacci sequence has this relation, right? It's an plus 2 equals an plus 1 plus an, right? You store it in a series, right? You get the sum an plus 2 x to the n plus 2, n greater than or equal to 0, plus the sum, equals n greater than or equal to 0, an plus 1, x to the n plus 2, plus an, x to the n plus 2, right? N greater than or equal to 0. And then this is just the same thing as f of x minus the first two terms, right? So this is minus a1 x minus a0. This is x times f of x minus a0. And this is just x squared times f of x. I went like full speed on that. So hopefully, let's see. Can we use the same question to get the total amount we paid over 30 years? Absolutely, you could. Just set A0 to be 0 and do the same thing. So hopefully that answers your question, LMAO. So Mohammed Arib says, Davra, can I ask what I studied in university? So I got my PhD in 3 and 4 dimensional geometry at Caltech. I've been a math person the whole way. So I did my undergraduate degree at Cornell, where I studied math. And back then I liked combinatorics and stuff. But as I went to graduate school, I got into like knot theory and 3 and 4 dimensional geometry. So that's what I got my PhD in. But I just always really love talking about math to people. So it's always what I wind up doing in in one way or another. But in any case, A0 is the same as A1 in the Fibonacci sequence. So after some quick cancellation, you'll figure out that f of x is actually 1 over 1 minus x squared. Okay? Do the same thing again. Do the partial fractions here after factoring the denominator, and you'll get the Binet formula for the Fibonacci numbers. Okay, but we've talked about this already, so I don't want to spend too much time on it. Let's talk about some interesting things that happen when you multiply generating functions with each other. Okay, so let's go on to problem number 2. So if you weren't here when I was stating problem number 2, what is going to happen? So what was problem number 2? So usually you have 2 standard die, right? You have 2 standard die. They're 1, 2, 3, 4, 5, 6, and then the other die is also 1, 2, 3, 4, 5, 6, right? So these are 2 standard die. Write down the number of ways there are to get all numbers when you roll both, right? So if you roll both die, there's one way to get a 2, right? So here, this is the number, and this is the number of ways to get it, right? So how many ways are there to get a 2 if you roll 2 die? There's only one way. How many ways are there to get a 3? Well, there are 2 ways. How many ways are there to get a 4? Well, there are 3 ways. How many ways are there to get a 5? Well, there are 4 ways. How many ways are there to get a 6, 5, 7, I believe 6, and then 8, 5, and then 9, 4, 10, 3, 11, 2, and 12, 1. Okay? So if you take 2 standard die, this is the list of each number you can get as a total, and on the right is the number of ways you can get that particular number. So let me know if that makes reasonable sense. And so my question to you, if you choose to accept it, is there another way I could label these dice so that that table would be exactly the same? So I have, again, 2 6-sided die, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and I would like to fill in numbers here. Is there any way to do this so that there's still only one way to get a 2, 2 ways to get a 3, 3 ways to get a 4, and so on and so forth? And you would not be surprised to hear that like the idea of storing a sequence in a polynomial or in a power function is going to play a role here. So let me know if there are any ideas about this, about how you might do this, or if there are any questions about this. And then I will start to. We have still have 2 6-sided die, and the question is there any way to fill out the numbers? I will say one thing to you, which is that each number has to be a positive whole number. A positive whole number. Yes. And yes, good question, Ken. So I'll give it a minute or two. Zach Starr did a video on this. I don't know who that is, but I'm more than happy to check it out. That's very good. My intuition says there's no other way. Okay. We have one answer. Okay. All right, I'm about ready to get going. This is one of the things that makes this like a weird format is I have to give the answer. Unless there's a immense demand that I hold off on this. So people are saying intuitively it seems like there should be no solution. Okay. So here's what I would like to say, which is that there is a solution. There is a solution. The person who came up with it is a person by the name of, hold on, let me pull up his name so I don't spell it wrong, is Sicherman. And so I guess the person who came up with these die is a person by the name of Sicherman, and the die are called Sicherman die. Okay, so Ken says he has no idea how to apply generating functions to this. So what we've done so far is, we've kind of figured out how to store a sequence in a generating function. But I want to point something out to you, which is kind of interesting, which is what happens when you multiply two generating functions. Okay, so how about this? How about I make a generating function for a standard die? Okay, here's my standard die generating functions. Okay, the standard die generating function, I'm just going to say is 1 plus x. Oh, sorry, is just going to be, let's say x plus x squared plus x cubed plus x to the 4th plus x to the 5th plus x to the 6th. Okay, this is going to be my standard die generating function. Okay, so what am I talking about? Why is this the standard die generating function? Well, I'm basically trying to store a sequence in a polynomial in a reasonably clever and intuitive way, and the idea is pretty simple. The idea is, in this case, how many ways if I just roll a single die, how many ways if I roll a single die are there for me to obtain a 3? Well, there's only one way, and that's exactly what the coefficient is telling me. Okay, how many ways are there on a standard die to obtain a 4 if I just roll that one standard die? There's only one, and that's exactly what the coefficient is telling me. Okay, how many ways on a standard die are there to roll a 5? Once again, one, and that's exactly what the coefficient is telling me. And same for every number, right? That's why the coefficient of all the numbers is 1. And you can actually think of this as an infinite generating function. It's just that most of the coefficients are 0 because there's no way to obtain most numbers when you roll a standard die, right? But here's my question to you. What happens when you multiply dx with itself? And this is a very powerful concept because it applies when you multiply two generating functions in general. So we have to think very carefully about this. If I multiply d of x with itself, I want you to notice what happens. So you have x to the 1 plus x squared plus x cubed plus x to the 4th plus x to the 5th plus x to the 6th. Okay? And we are multiplying it with x to the 1, x squared, x cubed, x to the 4th, x to the 5th, x to the 6th. Very interesting. So if I multiply this, the coefficient of x squared now is going to be 1 because there's only one way to get 2 by multiplying this one and this one. Huh. The coefficient of x cubed is going to be 2 because there's only 2 ways to get 3. I can multiply this term with this term and this term with that term. Interesting, right? And the coefficient of x cubed is going to be 4 of x to the, what am I doing? The coefficient of x to the 4 is going to be 3. The coefficient of x to the 5 is going to be 4. And the coefficient of x to the 6 is going to be 5. Then 6 x to the 7th plus 7 x to the 8th plus, of course, I'm like losing my mind today. You should never do math in front of other people. Just a word of advice. So 5x to the 8. Because how many ways are there to get 8? Well, you can add a 2 and a 6, a 3 and a 5, a 4 and a 4, a 5 and a 3, and a 6 and a 2. So you get 5x to the 8 plus 4x to the 9th plus 3x to the 10th plus 2x to the 11th plus x to the 12th. How interesting that the numbers, when I multiply these two generating functions, are precisely the numbers from the table. In fact, when you multiply two generating functions, it actually gives you the same information, okay, as how many ways are there. If you take one thing from the first and another thing from the second, how many ways are there to get that total, okay? So multiplying generating functions, so for example, the coefficient of x to the 9 is the number of ways you can total 9 if the number of ways to get any individual number are the coefficients given to you by the original generating functions. Okay? So I want to really impress this point upon you because it is quite powerful. Okay? We're going to use this later on to make change for $1. So if there are any questions about this at all, just take a minute with it. Why is it that the numbers, like the coefficients here, are precisely the ones given in our table when we wrote out how many ways are there to get every number when you roll 2 die? Okay? So, if there are no questions about this, I'm going to continue on. Okay. Now I would like to use 2 different die. Okay? The new die are going to have their own generating functions. So you have g of x for one of them, right? And h of x, let's say, is the generating function for the other die, okay? So remember, what would it look like? So for example, if my die were like 2, 2, 3, 4, 5, 6, let's say, what would the generating function for this die be? Well, it would be 2x squared plus x cubed plus x to the 4th plus x to the 5th plus x to the 6th. Because on this die, there are 2 ways to get a 2, there's 1 way to get a 3, there's 1 way to get a 4, there's 1 way to get a 5, and then there's 1 way to get a 6. Okay? So you can take any die and turn it into a generating function which counts the number of ways you can get that specific number. Okay? Hopefully that makes sense. But here's the thing. If I have 2 die, g of x and h of x, then what must their product be? Their product must be exactly this, right? Because the table for these rolling these 2 die must be exactly the same as the product here. So in fact, g of x times h of x must be x plus x squared plus x cubed plus x to the 4th plus x to the 5th plus x to the 6th quantity squared. Okay? Let me know if there are any questions at all about that, okay? Because now what we can do is we can factor the right-hand side to try and figure out what are the possibilities for our 2 die g of x and h of x, okay? So if I factor the 2, what's it going to be? Like, it's going to be, well, there's going to be an x squared, for sure, right? I can pull out an x squared, right? And then I'm left with a 1 plus x squared plus x cubed plus x to the 4th plus x to the 5th. I think negative 1 is going to be a root of this. So it's going to be x squared. Yeah, it is, because it's a odd degree, and yeah, it's all okay. So x plus 1 squared, and then I need to do synthetic division. Let's see, 1 1 1 1 1 1 and then negative 1. Let's see, 1 minus 1 0, and then 0 1, and then minus 1 0 0 1 minus 1 0. It worked. So this becomes 1 plus x squared plus x to the 4th quantity squared. Okay, 1 plus x squared plus x to the 4th is, I believe, beyond my factoring capabilities. So I'm just gonna open Mathematica and factor 1 plus, let's see, factor 1 plus x plus the fourth x squared. Okay, it's 1 minus x plus x squared and 1 plus x plus x squared. Okay, so you get this is equal to x squared times x plus 1 squared, and then 1 minus x plus x squared squared, 1 plus x squared squared. Okay, please do let me know if there are any questions at all about this. Okay, so g of x times h of x is equal to this. Okay, but now here's the thing. All I need to figure out is a way to distribute these factors among g of x and h of x. I can try all the different ways and see if any of them works. And if they work, I will know that there's a way to construct these die g of x and h of x. Okay? And if it doesn't work, then I'll know. In hindsight, we could have done... Should we understand... Okay, hold on, I'm getting a lot. Should we understand why we went this far? It's sort of like if I say to you that A times B equals, I don't know, 75, right? Then what you do is you rewrite 75 as 5 times 3. And then you, to think about what the possibilities for A and B are, you think about which one got the 5s and which one got the 3s, right? And so that's exactly what I'm doing here, right? So basically, all our possibilities for g of x and h of x must come from, one of them has to get some of these factors, and the other one has to get the other of these, the rest of these factors, okay? And it turns out there is a way that works. There is a way to assign some factors to g and some factors to h in a way that gives you two working die. You can just set g of x equals x times x plus 1 times x squared plus x plus 1, which gives you x plus 2x squared plus 2x cubed plus x to the 4th power, okay? And you can assign the remaining factors to h of x, which will give you x times x plus 1 times x squared plus x plus 1 times x squared plus x minus 1, and then this will be x plus x cubed plus x to the 4th plus x to the 5 plus x to the 6th plus x to the 8th. And so these two are going to be our dice that are going to work. Okay? And there it is. That's how you, this would be a brutal thing to guess and check your way through, right? But with generating functions, all we had to do is figure out which factors went where. And I'll just tell you, if you did some work with this, you would see that these two factorizations work. So the alternate versions of the die that'll give you the same totals are, let me write them out. You have the payoff. It's going to be 1, 2, 2, 3, 3, 4, and 1, 3, 4, 5, 6, 8. And there it is. Try it. You get the same, that's wonderful, Weak Sauce. Happy to hear it. In any case, there it is. You'd have many factor combinations, but remember, we're only looking for combinations that would give you 6 terms, right? So that really narrows it down, right? So you would only want factor combinations that gave you exactly 6 terms when you multiplied them out. So that narrows it down by a lot, and it's actually not that much work to check which factor combination. Yeah. So anyways, these are the Citroen's dice. Okay. I'm already an hour in, but I did say that I would tell you how to make change for $1. This one's a classic, and so the fastest way to make change for $1 is to ask the fastest way to figure out how many ways there are to make change for $1 is to ask your computer to Taylor expand a function. It turns out, which is kind of insane. But here's how this is problem 3. actually, I advertised two problems. One was if order matters. And the other is if order does not matter when making change. Let's do the order does not matter situation first, okay? So in the order does not matter situation, if you're making change for 6 cents, let's say 1 cent plus 5 cent coin is the same thing as using a 5 cent and then a 1 cent coin. All that matters is the number of each coin that you used, right? If the order does not matter. Now, there's a famous article, I forget who wrote it, but someone just put it in a newspaper, I think, and said that there were 293 ways to make change for $1 using 1 cent, 5 cent, 10 cent, 25 cent, 50 cent, and $1 coins. And of course, this is an old article, which is why I guess that maybe there were more 50 cent and $1 coins in circulation in the past. I'm not even sure people use coins anymore, so this already might be a very outdated way to state this question. But using these coins, the answer is 293. But of course, I want to give you the most general approach possible, right? Okay, so here's what I'm going to do. I'm going to make, let's say for now, we're only using pennies, nickels, dimes, and quarters. Why not? Okay. Well, here's what I'm going to do. Just like with the dice, remember what we did with the dice. The product of the two, very good, Ken. The product of the two generating functions, right, should tell you the number of ways you can make that total, right? Remember that from the last question, right? So let me ask you something. What's going to be the generating function if you were only allowed to use pennies? If you were only allowed to use pennies, well, if you're only allowed to use pennies, you can think of this as just like the one die situation. Well, you can make change for any number of cents, and you can only do it in one way. You can make change for nothing in one way. You can make change for a 1 cent in one way. You just use your 1 cent. You can make change for 2 cents in one way because you use both. Like you use 2 pennies. You can make change for 3 cents in one way. You use 3 pennies. You can make change for 4 cents in one way by using 4 pennies, and so on. Okay. This is going to be 1 over, this generating function compresses to 1 over 1 minus x. Okay. Now let's figure out the nickel generating function. The nickel generating function is only answering the question, how many ways are there to make change for n cents if I am only allowed to use nickels? Okay. Well, I can make change for 0 cents in one way by not using any nickels. But then there's a gap because I can't make any change for 1 cent, 2 cent, 3 cents, 4 cents using nickels, right? I can make change for 5 cents using 1 nickel, right? And I can make change for 10 cents using 2 nickels. So there's only one way to do it. And I can make change for 15 cents using 3 nickels. Again, only one way to do it. And so on. And it's not too hard to see that this is just going to be 1 over 1 minus x to the 5. How did I get that? Just plug x to the 5 in the one above. Okay? Now let's come up with a generating function for dimes. Similarly, it's going to be 1 plus x to the 10 plus x to the 20 plus x to the 30 and so on. So this is 1 over 1 minus x to the 10. And the one for quarters is going to be 1 plus x to the 25 plus x to the 50 and so on. And this generating function is going to be 1 over 1 minus x to the 25. Okay. So amazingly, the number of ways to make change for $1 using all these coins, if order does not matter, is just going to be the product of these generating functions in the exact same way that we were talking about the dice earlier. I mean, how insane is that? So this is just going to be px, nx, dx, qx. You just multiply these, okay? You can compute their Taylor expansion. You can ask your computer to do it. And the coefficient for n the coefficient for x to the n in the Taylor expansion of the right-hand side will be exactly the number of ways you can use these 4 coins to make change. Okay, so let's do it. I mean, maybe you don't believe me. So, and it's so easy. By the way, this is often a programming interview question that's given, and you're supposed to use dynamic programming. But I feel like the best answer to this question is say, pull out my calculator and ask for the Taylor series of 1 over 1 minus x, 1 minus x to the 5th, 1 minus x to the 10th, 1 minus x to the 25th. Okay, and so there was some conversation about this, so please give me the Maclaurin series of this. Give me the first 400 terms, why not? Boom. And so then look for the coefficient of x to the 100. Where is it? X to 100. There are 242 ways to make change for $1 using these 4 coins. 1 line of code. How nice is that? If you are allowing yourself to use 50-cent coins and $1 coin, all you need to do is throw it in. So x to the 50, and then 1 minus x to the 100. And just like that, there are 293 ways to make change for $1 using pennies, dimes, nickels, quarters, half dollars, and full dollar coins. Isn't that amazing? So there it is. That is a 1-line answer for just, and by the way, this is the crazy thing about it. It's not just an answer for $1. You can look up any number here. So for example, how many ways are there to make change for 349 cents using these coins? And it turns out there's 21,350 ways to do it, assuming order does not matter. I know. Beautiful, isn't it? Okay. I said I would also tell you how to deal with the situation where order matters, okay? How do you deal with the situation where order matters? Okay, well, let's talk about this for a second. So we can't do things the way we did them before because now order matters, right? So basically the way that we divvied up our generating functions before, we had one for pennies, one for dimes, one for nickels, and one for quarters, right? Because that's all it is, to divide $1 into coins when order does not matter. And thank you all for the kind words. So all you need to worry about is how many pennies are there, how many nickels are there, how many dimes are there, how many quarters are there. But if, for example, you are dealing with a situation where order matters, you're actually dealing with more like sequences, right? You're actually dealing with the sequences. This is still susceptible to generating functions, but you just have to think a little bit differently. Okay, so here's the question that I am going to ask you. How many ways are there to make change for n cents using 1 coin? I'm going to start by writing down this generating function. Okay, so remember, I'm doing the problem now where order matters, and hopefully it makes sense to you why the approach I just had is not going to work. Okay, so I'm making change for n cents using 1 coin, and my 1 coin can be any from the list. So I have pennies, dimes, nickels, quarters, but you can use whatever coin set you want. It doesn't matter. So the first comment on this video was, I'm annoyed because you're only using American coins, but yeah, I swear this methodology works, whatever you do. So my coin set is, pennies, nickels, dimes, and quarters. Okay, and my starting question is, how many ways are there to make change for n cents using only one of these coins? Using only one of these coins. Okay, well, there's no way to make change for 0 cents. Well, actually, I should have started with 0 coins. So how do you make change for n cents with 0 coins? This is a dumb question. The only thing I can make change for with 0 coins is 0 cents. So this is just going to be 1. And the coefficient of x to the 1, x to the 2, everything onward will be 0. Because the only thing I can make change for with 0 coins is 0 cents. So that's where this one is coming from. Okay. Let me ask the next one. How many ways can I make change for n cents with 1 coin? Okay, so I'm making change for n cents with 1 coin. Well, now I'm allowed to use 1 coin, so the only thing I can make change for is like 1 cent. So I get an x because there's one way to make change for 1 cent using one of these coins. There's also one way to make change for 5 cents using one of these coins, and one way to make change for 10 cents using one of these coins, and one way to make change for 25 cents using these coins. Okay. Now let's see how much each of you are following. So now what if I wanted to make change for n cents with 2 of these coins? What would that be? Let me know if you have any guesses. I'm probably going to say it in like a minute anyway, but how many ways could you make change? What would the generating function be for the number of ways to make change for n cents using 2 coins, where the list of coins I'm allowed to use is up top. Okay. I'll remind you, this is completely analogous to the dice situation. Okay. There it is. John Chesson has the answer. But let me, please stop me, any of you, if you have a question about this. But yes, you are exactly right. It's going to be x to the 1 plus x to the 5th plus x to the 10th. That's exactly, okay. It seems like everyone is following. I'm very happy about that. So squared and so on. So I have a general answer now, which is the number of ways to make change for n cents with k coins will just be this, right? X plus x to the 5th plus x to the 10th plus x to the 25th to the k. This is going to be the number of ways to make change for k cents using, what am I saying? For n cents using k of the above listed coins, okay? So if I'm allowed to use any number of coins, and watch me carefully now, if I'm allowed to use any number of coins, wouldn't it just be the sum n greater than or equal to 0 of x plus x to the 5 plus x to the 10 plus x to the 25 to the n? I would just have to add them all up, right? So if I'm allowed to use now any number of coins, then I just need to add all the work I've done so far. Hopefully that makes perfect sense, right? So by the way, this sum is just like 1 plus, x plus x to the 5th plus x to the 10th plus x to the 25th, right? Plus the same thing squared plus the same thing cubed and so on. Squared and then cubed and so on and so forth. Any idea how to compactify this? I should not be using the word compactify willy-nilly, but any ideas about how you write this as just as something shorter, not an infinite sum? So remember, this is the generating function for when I'm allowed to use any number of cents, order matters, okay? Well, I have it set on low latency, but there could be a delay, but this is just going to be 1 over 1 minus x plus x to the 5th plus x to the 10th plus x to the 25. There it is. Okay, Mohammed got it. Okay, so guess what? If you're interested in the number of ways you can make change for any number of cents using these 4 coins where order matters, all you need to do is ask your computer to do the Taylor expansion of this function. Okay, so all you need to do is ask it to do the Taylor expansion of this function, which is, again, completely insane. So watch me now. So series 1 over 1 minus x to the 5th minus x to the 10th minus x to the 25th. Let's do maybe the first like 30 terms, because this will grow much faster where order matters. Okay, so you zoom in a bit. Okay, these are the answers my computer is giving me. Let's see if we believe them. So for example, right now, this methodology is telling me that the number of, hold on, I'm slightly cut off here, that the number of ways to make change for 10 cents is, there are 9 ways to make change for 10 cents if order matters. Okay, let's see if we believe this. Are there 9 ways to make change for 10 cents using these coins if order matters? Well, yeah, this is for real. So this is going to be 10, that's one way, right? 5, 5, that's another way. But then you could do like 1, 1, 1, 1, 1, 5. But then you can put the 5 wherever. So you could also do 1, 1, 1, 1, 5, 1, 1, 1, 1, 5, 1, 1, 1, 1, 5, 1, 1, 1, 1, 5, 1, 1, 1, 1, 5, 1, 1, 1, 1, 1. There it is. 1, 2, 3, 4, 5, 6, 7, 8. Uh-oh. What happened? Change for... Oh. It's all ones is the 9th way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right. There are 9 ways. And so I guess my point is, you see, this is a lot less effort than ready. Yes, I'm sorry, I missed it. Everyone seems to have gotten it before me. So, man, isn't that amazing? So, yeah, you just look at the terms in the expansion of this, and then wow, what do you know? It gives it to you. I'm kind of curious what happens if you do take this to the 100. It's probably going to be way bigger. Okay, there are. Let's see. So this is 1,000. This is 1,000,000. This is 1 billion. This is 1 trillion. So there are 8 trillion, 577 billion, 828,731,901 ways to make change for $1 using these 4 coins if order matters. And it's alarmingly easy to add in coins of different denominations. You would like to see the 2 functions. Yeah, so here's the... Here, I'll erase the outputs. So this top one is... whoa, what am I doing? What am I doing? Being silly. Erase this. So this one above, here, let me erase a series as well. So someone asked to see the 2 functions side by side. Here we go. This one is where order, whatchamacallit, does not matter, and the one below is the one where order does matter. So let me know if that answers your question, weak sauce. And honestly, I think that's it out of me today. I did have some more stuff, but whatever. We can do it next time. So I hope you all really, really enjoyed the stream. Thank you all so much for showing up. And yeah, I'll see you all on Saturday. I'll be streaming at the same time, 1 p.m. And peace.